Hi everyone, in this video we'll start working a little more on the details of figuring out what the graph of a polynomial looks like by hand. So instead of relying on our calculator to show us pictures, which sometimes it does well and sometimes it doesn't, we want to be able to get a rough sketch without our calculator. I do want to be really clear up front that this is kind of a limited method that we're going to work on. We basically want to, by the time we're done, be able to graph any factorable polynomial. So if it's given to you factored, or if you know enough to factor it yourself, you should be able to sketch its graph. And we're going to rely on the factored form to help us find zeros so that we know where the x-intercepts are, which will tell us approximately where the local maximums and minimums are. Not exactly, but approximately. So this is not perfect. There are tons of polynomials that we won't really be able to do a good job of graphing until we hit calculus, but it's a start. And our big goal is just to have a good idea in our head of what polynomials generally look like. So it will do that for us. Okay, so this first one is given to us in factored form, which saves us a little work. As soon as you have something in factored form, you can imagine if you set that equal to 0, what would you get? So you would get a -5, a 3, and a 6, which means the x-intercepts of function j are -5, 0, 3, 0, and 6, 0. Okay, the other thing we'll need, so basically we're going to use a combination of our local behavior, which for polynomials really is just our zeros, and in the next video we'll start talking about the multiplicity on the zero, because that will be one last detail that we want to add. But for now, just the local behavior is the zeros. And then we also want to know what our global behavior is just to get us started so we know how to connect the dots once we have our zeros there. So here, because it's in factored form, the x-intercepts are easy, but the global behavior is slightly disguised. We have to imagine multiplying this out and what product would give us our highest power on x. So multiplying the x term in each parenthesis together is going to give us the x cubed, which is the highest power we should get out of this. So if we multiply an x by a negative x by an x, we're going to get a negative x cubed. So our global behavior should be a y equals negative x cubed. Okay, so cubic function, and the negative is important. You do want to keep track of that coefficient. I don't care if there's a 2 or a 3 or a 1/2 out in front, but I do care whether it's positive or negative because that will determine which direction our arrows go. So an x cubed is an increasing function, and negative x cubed is decreasing. This does not mean that my graph will look just like this. It just tells me the global behavior. So as I get out to the ends, it tells me where to put the arrows. There should be an arrow going to the top left and the bottom right. All right, so this is all the info we're going to get. And we're going to pair this with the idea yesterday about what the graphs of polynomials look like to try and get what is just, again, a very rough sketch. This is not supposed to be perfect on all the details, but just the general idea of what this thing looks like. Okay, so at 3, at 6, and at -5. So arrows, we know to put an arrow up to the left. So we're going to come from positive infinity on the left-hand side, and we need to come down and cross through the x-axis at -5. We will see interesting shapes in the next one where sometimes we bounce off at the intercept or we make a flat spot. But for this example, I've deliberately chosen things only that cross straight through the axis. So we'll head down for a little while, and then eventually we have to turn around and come back up and cross at 3. And then we'll head up for a little while and eventually turn around and cross at 6. And then our global behavior should take back over again. We've used up all of our local behavior, and we're going to head to negative infinity. Okay, so again, I don't expect this to be anything perfect. I don't know exactly how far below the x-axis this goes or how far above the x-axis this goes. I do know that it was cubic, so if I've got 3 zeros, that's all of them. If I've got 2 turning points, that's all of them. That's the maximum possible for a cubic. I know that my global behavior is right, And then remember just the more general details. Polynomials are smooth and continuous. Continuous meaning it's one continuous piece. You don't have to pick up your pen when you draw it. And smooth meaning there are no sharp corners. So mine might even be a little rounded. As your degree gets higher, these sometimes are a little bit steeper, but there should never be a sharp corner. And I will mark you off if you give me sharp corners on polynomials. The other thing that I could point out here is just something to be aware of. When we graph a quadratic, we know the vertex is exactly in the middle of the two x-intercepts. As soon as you hit a third degree or a fourth degree or a fifth degree, that's not going to hold anymore. So I don't need you to know exactly where this is, but I do want you to be clear on the fact that you can't assume it's directly in the middle. I think mine probably looks like it is even, but I just don't want you to make that assumption. So it should probably be a little further over here. And same with this one, it won't be at 4.5 that I expect to hit my maximum. I would expect to hit it a little over from that. So fine if your graph isn't perfect, as long as you don't leave with the wrong impression thinking that the local maxes and mins are always in the middle of x-intercepts. Sorry if I'm repeating myself here, but I do want to say that I very deliberately didn't label the vertical scale. That's just me saying I don't really know exactly what the y values of this are, but I know this is the general shape. Okay, so the other two are not factored for us, so it's really just about factoring tricks, and then the graphing part is exactly like what we did up above. So since this one is in standard form, I can snag the global behavior really easily. So let me just go ahead and write that down right now while I'm looking at it. The global behavior should be a y equals x cubed. If you want to say 3x cubed, that's completely fine. It doesn't matter. It doesn't change the picture in my head. The picture in my head should be right side up x cubed, which means my arrows should go down on the left side and up on the right side. And again, that's all it tells me. It doesn't tell me that the middle of the graph will look like this. I doubt it will. It'll have the curves kind of like up above, but it does tell me where to put the arrows. Factoring trick number one, when you have 4 terms and you're trying to factor, one thing you can do is factor by grouping. I'm actually going to catch myself right here. You have some choices here. You could just group right away, but if you spot it, I think it makes life a little easier if you factor out the 3 right off the bat. So if you don't, you can factor it out later. It won't be a dead end for you. It's just nice if you look first for a common factor. Okay, so now the 3 is fine. I'm just going to leave it out there. What I want to do, here, let me make this brackets for a little bit so that it's easier to tell where things are, is group these into 2 pairs. And you can try rearranging terms to see if you like the way things work out better, but generally if we have these in descending order, it's probably not a bad idea to just try it with the order you've got. So in the first group, I can factor out an x squared, and I'll be left with an x minus 4. Remember, you can always distribute back in to double check yourself. In the second group, I can factor out a 4. I want to be really careful here because that minus is in front of the 4. As soon as I throw these parentheses in, it makes it apply to the second term as well, which means this should actually switch to a minus. Remember, you can multiply it out negative 4x squared plus 16 to check yourself. Another way to think about this is factoring out a negative 4 means you're dividing it out of each term. So if we divide negative 4x by negative 4, we just get x. If we divide 16 by negative 4, we get negative 4. Okay, so really crucial for grouping is that these are the same. So this is what you'll be looking for. If that doesn't happen, then your grouping is not working for you. So here, I think a lot of people can reproduce factor by grouping, but I think that it's not uncommon for people to not really be clear on what's happening, so I'm going to try and make it clear. This subtraction right here is inside the brackets. It's the big operation. So if you plugged in numbers for x, you'd do a bunch of arithmetic in parentheses, and then you'd multiply, or you'd square early on as well, and then you'd subtract. It's the very last thing happening, which means that this is written as the difference between 2 terms. The terms are messy. Each term contains 2 or more factors. Inside one of the factors, we have another difference. But the big thing here is the difference between 2 terms. So we want to kind of think back to if I had an ax minus bx, I could factor out a greatest common factor. And this is really the same problem. It looks messier, but our a is the x squared, our b is the 4, and instead of x's, we have x minus 4. So we can factor out the x minus 4, and we will be left with, here again, we can keep the brackets if you want to see that separation, the x squared and the minus 4. At this point, it's okay to just drop the brackets. The brackets are indicating that we need to multiply by 3, and just having the parentheses there will already do that. So we don't really need them. It's not bad if they're there necessarily, but I'm going to drop them. I do want to do a little better with the x squared minus 4. That's a difference of squares, so it factors into an x plus 2x minus 2. Okay, so there's the factoring. So remember, factor by grouping. If I now want to look at 2, -2, 4, my zeros are at 4, at -2, and at 2. My global behavior is right side up x cubed, so I should start on the left at -infinity. I'm going to cross through at -2. I'm going to cross through at 2. I'm going to cross through at 4, and then head off to positive infinity. Again, don't assume that the maximum is right in the middle. That's generally not true. A really quick check that you could do for yourself just to see if you're upside down or have some glaring big mistake, you can always go ahead and find the y-intercept of the graph. It's really easy in standard form. If you plug in 0 for x, it wipes out all 3 terms. You just get the 48. So our intercept should be at positive 48. So we are at least on the right side of the x-axis there. It's a little trickier if you're in factored form, but certainly not anything terrible. You just plug 0 in for x and you'll get 5 times 3 times -6. So 18 times 5, 90, -90. So we should be well below the x-axis. So again, that's a quick check just to see if you accidentally got your graph upside down or got part of it upside down. Okay, last one. And again, this is really just about showing you your factoring tricks. So this one is not a good candidate for grouping. I don't necessarily have a common factor, but I think I will factor out a -1 just because it always makes life a little easier to factor if you don't have the negative attached to your leading term. Did I get them? Yep, okay. So the trick here is, even though this is not quadratic, it has a very similar structure to a quadratic. It has 3 terms. One of them is constant, one has a variable, and one has the square of a variable. So even though it's not quadratic, we can use this unfoil method, this little bit of trial and error, to get this thing factored. If I want to split up an x to the 4th, I'm going to make it an x squared and an x squared. This means when I multiply those two, I'll get my x to the 4th. And when I multiply my inside outside by whatever constants go here, I'll get an x squared term and an x squared term, which matches up with this -12x squared I'm hoping to get. So all I have left to do is split up factors of 27 to try and get that -12. That's sounding like it should be a -3 and a -9. That x squared minus 9 is definitely factorable. That's another difference of squares. Make sure you watch for difference of squares. I always think I'm being nice when I give a difference of squares, but sometimes people forget to look for them and they get really stuck. I would be completely fine if you quit here, but I do want to point out that there is no rule that says when you factor, you have to end up with integers or rational numbers. Oh, what did I do? I filled in my hole here. We're going to shrink and see if I can squeeze it in there. So you could think of this as a difference of squares as well. It's just that the number that you have to square to get 3 is the square root of 3. So you could, don't have to, but you could break this into an x plus root 3, x minus root 3. If you don't like that or you don't spot that, it's okay. We're really worried right now about getting the zeros. So I can read off from the last 2 factors that I'm going to have zeros at -3, 0, and 3, 0. And then you just might have to do a little work for this other factor. You would say, okay, I also need to know when x squared minus 3 is equal to 0. And if you can just spot that, great. Otherwise, you can solve x squared equals 3, which means x is plus or minus the square root of 3. So it's the same thinking I used to split up the factors. Basically, if you know you have a 0, there should always be a corresponding factor that you could write down. And if you have a factor, you should always know a 0 based on that. So this is going to be a root 3, 0, and a negative root 3, 0, 0. Okay. I skipped global behavior. Let's go ahead and do that really quickly because this first version of the equation is in standard form. We should just be able to read the global behavior right off. So you look for the highest power, and then you also look at the coefficient. So I'm expecting a negative x to the 4th, which is this kind of shape. So I expect my arrows to go down on both left and right hand sides. Let's see. Okay, so if we go out to 1, 2, 3, negative 1, 2, 3, we should have zeros at plus or minus 3. We also have zeros at plus or minus the square root of 3. So, and I have this in here from when I was playing around with this before. You can go to your calculator and ask it for a decimal approximation just so that you have a better idea of where to put the point. So the point should go around 1.7. When you label it, go ahead and use that exact. This is right at square root of 3. This is right at negative root 3. Then we can use our global behavior to say we should start at negative infinity, cross at negative 3, cross at negative root 3, cross at 3, cross at negative, cross at root 3 and cross at 3. I'm saying the wrong things as I go here. Okay, and again, this is just rough shape, but that's all I'm looking for. This appears to be even, and it actually is. I can tell because if I plug in a positive x value, say I plug in a positive 2, I'm going to get negative 1 times 2 to the 4th plus 12 times 2 to the 4th minus 27. If I plug in a negative 2, that negative 2 is going to get raised to the 4th power, so it's going to become exactly the same as when I plugged in a positive 2, and the same thing here, it gets squared. So all the even powers end up wiping out the negative sign so that you get the same thing whether you plug in the positive or negative version of a number. So in this case, this minimum should actually be right smack in the middle. But these two, again, my graph, I think is kind of deceiving. I would not expect them to be. I would expect them to be pushed off to the outside a little. So just don't make that assumption. I'm not holding you responsible for figuring out where they are. I just don't want you to be assuming they're in the middle. All right. Thanks for watching.